A very warm welcome to all of you who are watching this video. Our next topic is relations and functions, the first chapter of class 12. Today we will study about what is a relation and how do we find the domain, codomain and range of a relation. Now before we begin with what is a relation, you need to have a strong base of what is a set, what is a Cartesian product, and finally reach relation, which would be further extended to function. Now, how will we define a set? A set is a well-defined collection of objects. Means whichever collection you take, you get an unique answer. For example, the set of vowels A, E, I, O, U. So this makes a sense. That means you get an unique answer. Now moving on to Cartesian product. Suppose you consider two sets A and B. Now we are going to draw a connection between the two sets. A cross B. Cartesian product is written as A cross B. So this is the set builder representation of the Cartesian product A cross B. You can see the elements of the Cartesian product, that is A cross B, are in the form of ordered pairs, where the first element is from set A and the second element is from set B. So Cartesian product is defined to be all those ordered pairs where the first element comes from the first set and the second element comes from the second set. Now to understand this Cartesian product in a better way, we take a random example where set A has elements 1, 2, 3 and set B has elements A, B, C, D. So if we are saying it is A cross B, this means all possible pairs that you get beginning from set A and ending with set B. So let us draw the Venn diagram for A cross B. This is set A consisting of the elements 1, 2, 3 and this is B having A, B, C, D. So this set A has consisting of the elements 1, 2, 3 and set B consists of the elements A, B, C and D. Now if we talk of 1, it could be connected to 1A, it could be connected to B, it could be connected to C and it could be connected to D. So let us do it. 1 is connected to A, 1 is connected to B, 1 is connected to C and 1 is connected to D. Similarly, beginning with element 2, it can be mapped with A, it can be mapped with B, it can be mapped with C and it can be mapped with D. So let us do it. 2A, 2B, this is 2C and this is 2D, right? Now beginning with 3, we once again connect each one of 3A, 3B, 3C and 3D. So 3A, this is 3B, this is 3C and this is 3D. So this is how we draw the Venn diagram for the Cartesian product of set A and B, that is A cross B, moving from set A to set B, and here we are getting the ordered pairs 1A, 1B, 1C and 1D, where the first element 1 is from set A and the second element is from the set B. Similarly 2A, 2B, 2C and 2D, and similarly 3A, 3B, 3C and 3D. So if you write the Cartesian product A cross B, it can be like this. So let us note down the elements of A cross B. As I told you, it is in the form of ordered pairs. So this will be 1 comma A, 1 comma B, 1 comma C and 1 comma D. Similarly, another 2 comma A, 2 comma B, 2 comma C, 2 comma D, then 3A, 3B, then 3C and 3D. So this is the Cartesian product of A and B, that is represented by A cross B. You can write it as moving from set A to set B. So these are all the ordered pairs where each first element is from the set A and the second element is from the set B. So this is an entire Cartesian product which moves from set A to set B. Please note, order in the ordered pair. Order in the ordered pair is important. So of course, A cross B and B cross A. A cross B and B cross A mean two different things. That is 1 comma A and A comma 1 are two different elements. So you cannot say that is A cross B and B cross A are same. Right. Now once we have the knowledge of the Cartesian product, let us extend this to a relation. So a relation is once again a connection between two sets A and B, such that relation is a part or subset of the Cartesian product A cross B. That means here in the Cartesian product we have taken all possible ordered pairs from A to B, whereas for a relation we will be a little selective, right? So in the Cartesian product you need to take all the possible ordered pairs, but in the case of a relation, as I am telling you that relation is again a connection between the two sets A and B, but here we have to be little selective in the sense that we cannot take all the ordered pairs that are existing in the Cartesian product. So we write the relation R A to B, where R is a subset of A cross B. R is the relation from set A to set B, and R is the subset of A cross B. That is the Cartesian product of the sets A and B. Now suppose I take the same example of set A and set B, where set A has the elements 1, 2, 3 and set B has the elements A, B, C, D. But this time we define it to be that my relation is such that we take all ordered pairs beginning with an odd number. That means we are not interested in the entire combinations that we get, but only as per the above definition. That is all the ordered pairs beginning with an odd number. So let us write the relation from A to B, where it is specific. That is the ordered pairs that will be taken in the relation. We have the first element, that the first element of the ordered pair as an odd number. So our set is, the Cartesian product is A cross B, that is 1A, 1B, 1C, 1D. So 2A, 2B, 2C and 2D. This is 3A, so 3B, 3C, 3D. So this is the Cartesian product A cross B. Now we are going to draw the connection between the sets A and B, and that set, that is a relation we are going to generate from this. Now under the specific condition that the first elements will be an odd number. So here you can see these are the four elements in the form of ordered pairs, where the first element is an odd number. Similarly this one. So we write the relation R as 1A, 1B, 1C, 1D, 2A, 2B, 2C and 2D. That means this is the relation under the condition that the first element of the ordered pair will be an odd number, right? Now, so this means that a relation happens to be a part of the entire Cartesian product. That means it is a subset of A cross B. As we have written earlier, that is R is the subset of A cross B. Now, in order to understand domain, range and codomain for a given relation, let us take a quick example. So let us take an example. Suppose I take set A as 1, 2, 3 and 5 and set B equals to 4, 6, 9. So set A 1, 2, 3, 5 and set B as 4, 6 and 9. Okay. Now R is a relation defined from A to B such that R takes up all those ordered pairs whose difference between the two elements of the ordered pair xy, if you consider this as xy, is an odd number, and needless to say that x must belong to set A and y must belong to set B. So we write the relation in the set builder form such as R is equals to x comma y, and what is the condition? That the difference between x and y is odd. So difference between x and y is odd, where obviously x belongs to set A and y belongs to set B. So this is written in the set builder form. Now let us write this set builder structure in the roster form. That means let us simplify it and write it in ordered pairs. So to pick up the combination, to start with 1. So let us write this set in the set builder form. So this is the this is the set builder form. That is R is the relation x from set A to set B. Now the different condition is the difference between x and y, that is the two elements in the ordered pair, should be odd. X belongs to A and y belongs to the set B. A is 1, 2, 3, 5. B is 4, 6, 9. So what is the Cartesian product? That is 1, 4, 1, 6, 1, 9. Then 2, 4, 2, 6, 2, 9, 3, 4, 3, 6, 3, 9, 5, 4, 5, 6, 5, 9. So this is the entire Cartesian product moving from set A to set B. Now our condition for getting the set for the relation is that the difference of the elements, that is difference of 1 and 4, like this is 1 minus 4 or 4 minus 1, that is coming to 3, which is an odd number. So our condition is that we'll take all those ordered pairs in the relation. That means all those ordered pairs will be included in the relation whose difference between the first and the second element is odd. So let us see which one are giving that particular condition. 1 minus 4, this is odd. 6 minus 1, 5, this will give you an odd number. 9 minus 1, 8, even number. 4 minus 2 is even. 6 minus 2, 4 is even. 9 minus 2, this is odd. 4 minus 3 is odd. 6 minus 3 is odd. 9 minus 3, 6, that is even. 5 minus 4 is odd. 6 minus 5 is odd. 5 minus 9 or 9 minus 5, that is even. So let us write the relation. The relation will consist of all those ordered pairs which are marked ticked. We have marked here. So 1 4 1 6 2 9 3 4 3 6 5 4 and 5 6 are the elements of the relation R. So R will have all these elements. So we can write R as 1 4 1 comma 6, then 2 9 3 4, then 3 6, then we have 5 4, and then we have 5 6. So 1 4 1 6 2 9 3 4 3 6 5 4 5 6. These are the ordered pairs which are included in the relation by the given condition. Now you can see here what the difference between how do we define the relation. As we have told, in the Cartesian product all the possible ordered pairs are included, right? So 1 4 1 6 1 9 2 4 2 6 2 9 3 4 3 6 3 9 and 5 4 5 6 5 9. These are all the possible ordered pairs that can be formed moving from set A to set B, and all these ordered pairs are included in the Cartesian product. So this is the Cartesian product, that is the ordered pairs moving from set A to set B, the entire ordered pairs. Now relation is, as you have already mentioned, is a part of the subset of the Cartesian product. Based on certain conditions, we have already told that we will be a little selective in the case of relation, which is a part or the subset of the Cartesian product. So you can see these ordered pairs 1 4 1 6 2 9 3 4 3 6 5 4 and 5 6. All these ordered pairs are part of this Cartesian product A cross B, right? So the above order, these ordered pairs are the part of the relation, and all other parts are not part of the relation, as the difference is an even number. Now after writing the relation from the set builder form to the roster or the tabular form, it is very easy to identify the elements of the relation R. Now domain is the set of all the first elements in the ordered pair. That means if we mark the first elements, they are 1 2 3 and 5. This becomes domain. That is, domain is equals to 1 2 3 and 5. 1 2 3 and 5, which happens to be the entire set A this time. Set A also we have set A is the same, that is 1 2 3 and 5. Moving on, talking of the range, it becomes the set of all the second elements in the ordered pair. That is 4 6 9 4 6 4 6. So the second element, the set of all the second elements in the ordered pair, here it is 4 6 9, repeated once will be taken only once, right? Therefore range is equals to 4 6 9, which happens to be the entire second set B. B was also 4 6 9. However, suppose we have some extra elements in set B which was not connected with any element of set A, then that element of set B will not be included within the range. Okay, so suppose we have some extra elements in set B which is not connected to any of the elements of set A, then that element of B will not be included within the range. And codomain is always the entire second set, that is set B. Codomain is the entire second set, that is set B. Now let us summarize this. The last example that we have taken, R is a relation from A to B. R is a subset of A cross B. That means R has got the elements in the form of ordered pairs on the basis of certain condition. Set of all the first elements in the ordered pair of R, that is domain, is 1, 2, 3, 5. We have taken the sets as A 1, 2, 3, 5 and B 4, 6, 9. So domain is the values 1, 2, 3, 5 which are the elements, first elements in the ordered pair of the relation. Set of the second elements in the ordered pair of relation is the range, that is 4, 6, 9. You can see the first elements 1, 2, 3 and 5 which are included within the domain, and the second elements 4, 6, 9 are included within the range. Repeated ones will be taken only once, right? And codomain is the entire second set, that is set B. So A 1, 2, 3, 5, B 4, 6, 9, that is R is a relation from A to B. Set builder form condition, R consists of all those ordered pairs in the form of X, Y. The difference between X and Y is odd. X obviously belongs to set A and Y belongs to the set B. The same thing written in the roster form or the tabular form, that is the elements of set R is 1, 4, 1, 6, 2, 9, 3, 4, 3, 6, 5, 4, 5, 6 based on the condition that the difference between the elements in the ordered pair is an odd number. Also note that the domain of a relation from set A to set B is a subset of this set A. Domain is 1, 2, 3, 5 is a subset of set A, and the range 4, 6, 9 is a subset of set B, because as we have told, in the range there might be some elements of set B which are not connected to any element of set A, and those elements of set B will not be a part of this range. So if we take 4, 6, 9 and suppose another element exists here 4, 6, 9 and the next number suppose 10, but 10 is not included in this range, right? So 4, 6, 9 is present in set B, so the range we can say of a relation from A to B is a subset of the set B. Now we are going to define the total number of relations that can be defined from set A to a set B. Relation, as we know, is a subset of the Cartesian product A cross B. So the number of relations is equals to the number of subsets of the Cartesian product A cross B. You know what is a subset, that you have already studied in set theory. If not, please refer to the chapter set theory and get the idea of what is a subset. So the number of relations is equals to the number of subsets of A cross B. Now the number of subsets we know is given by 2 to the power of the total number of elements present in the set, right? So number of subsets equals to 2 to the power number of elements of the set, that is equals to, here the set is A cross B, 2 power the number of elements of A cross B, and that is given by 2 power number of elements of A multiplied by the number of elements of B. Here it is n of A cross B, that is the total number of elements in the Cartesian product A cross B is equals to the number of elements in set A multiplied by the number of elements in set B. So 2 power the number of elements of set A into the number of elements of set B, and that is equals to 2 power n in n of A multiplied by n of B. This is the n of A is the cardinal number, that is the total number of elements present in set A multiplied by the total number of elements in set B. So the total number of relations that can be defined from a set A to set B is equals to 2 power the number of elements in set A into the number of elements in set B. Now see, if the set A has 3 elements and the set B is equals to 3, 4, 5, these are the elements of set B, set A has 3 elements, then find the total number of elements in the Cartesian product A cross B. So just now we have discussed that n, it is given that n of A is 3, that is the total number of elements in set A is 3. Total number of elements in set B, you can count 1, 2, 3, that is 3. So the total number of elements in the Cartesian product A cross B is equals to the total number of elements of set A multiplied by the total number of elements in set B. So we have, this is 3 cross 3 and that is equals to 9. So the total number of elements in A cross B is equals to 9. Let us see to the next question. Here let A equals to 1, 2 and B is 3, 4 are the two sets. Find the number of relations from A to B. So we have discussed already that the number of relations is given by 2 power the number of elements in set A multiplied by the number of elements in set B. So what is the total number of elements present in set A? 2. So you can write it as 2 power 2 multiplied by the total number of elements in set B, and that is also 2. So this is 2 power 4 and that is equals to 16. So the total number of relations that can be defined from set A to set B is 16. Moving on to the same question, similar question. We have question number 3 that let A equals to x, y, z and B equals to 1, 2. That means set A has 3 elements and set B has 2 elements. That is the cardinal number of set A is 3 and the cardinal number of set B is 2. Find the number of relations from A to B. As it is that we have done just now, the number of relations is given by 2 power cardinal number of set A multiplied by the cardinal number of set B. Cardinal number is the number of elements present in the sets. So this is 2 power number of elements in set A is 3 multiplied by number of elements in set B is 2. So it comes to 2 power 6 and that comes to 64. So the total number of relations that can be defined from set A to set B, set A having 3 elements and set B having 2 elements, is 64. Now let us understand what is called the inverse of a relation. An inverse relation is the set of ordered pairs obtained by interchanging the first and the second elements of each pair in the original relation. Now let us understand this by taking an example. Let us define a relation. Let the relation be 0, 2, 1, 3, minus 3, minus 2 and 2, 4. So this is the relation. Now what will be the inverse of a relation? As the definition says, it is obtained by interchanging the first and the second elements of each pair. So what is the inverse of this? So the inverse of this will be 2, 0, 0, 2 becomes 2, 0, 1, 3 becomes 3, 1, minus 3, minus 2, it can be written as minus 2, minus 3, and finally 2, 4 is written as 4, 2. So what is happening? This is interchanged. The first and the second elements you can see are interchanged. So 0 and 2 are interchanged. 1, 3 becomes 3, 1, minus 3, minus 2 becomes minus 2, minus 3, and 2, 4 becomes 4, 2. So this is what is the inverse of a relation. Moving on to the next question. Let the set A have the elements 1, 2, 3, 4 continue till 14. Now define a relation R from A to A. That is, the relation is defined from set A to itself and is defined as R is equals to all those ordered pairs which satisfy this condition, that is 3x minus y equals to 0, where x and y both belongs to the set A. Now you have to write down its domain, codomain and the range. So you have already come to know what is the domain, what is codomain and what is called the range. Domain is the set of all the first elements of in the ordered pairs of the relation. Codomain is the entire second set and the range is the set of all the second elements in the ordered pair of the relation. Now let us first see the relation. Here we can define the relation given as x, y, that is y is equals to 3x, x and y both belongs to the set A. 3x minus y equals to 0, so you can write it as y equals to 3x. Now if we take x equals to 1, what is y? Y is 3. If we take x equals to 2, then y is equals to 6. If we take x is equals to 3, then y is 9. If we take x equals to 4, then y is 12. If we take x equals to 5, then y is 15. But you can see 1, 2, 3, 4, 5 all are included within this set A. 3, 6, 9, 12 are available in set A, but 15 is not present or not an element of set A. So this particular ordered pair will not be a part of the relation. So our relation stands as R is equals to 1, 3, 2, 6, then we have 3, 9 and 4, 12. So these are the elements or the members of this relation 1, 3, 2, 6, 3, 9 and 4, 12. We need to find the domain. Domain is the set of all the first elements in the ordered pair of the relation. So we have 1, 2, 3, 4. 1, 2, 3, 4 are the elements of the domain. Range we know is the set of all the second elements in the ordered pairs of the relation, that is 3, 6, 9, 12. And codomain is always the entire second set. So we have here it is only one set, so it is 1, 2, 3 till 14. So this is the codomain. So now I think it is clear, very much clear to all of you. Just go through it and try to understand in case you got any doubt. Just review it, go through the theory part, that is domain, what is codomain, what is range, and everything will be clear. Now moving on to the next question, question number 5. Define the relation R on the set of natural numbers by R. The relation is defined as the ordered pair xy such that y equals to x plus 5. Now x is a natural number less than 4 and x, y both belongs to the set of natural numbers. We need to find the domain and the range. So before we can solve, let us first define this relation in the roster form. It is given in the set builder form, so always you need to define the set in the roster form. So again, let us first write down the relation given as x comma y is such that y is equals to x plus 5. Now it is given condition is x is a natural number less than 4. That is x is equals to 1, 2 and 3 and x, y belongs to natural number. So you can write that x is a natural number less than 4, so x is 1, 2 and 3. So let us now, we are given y equals to x plus 5. So when x is 1, what is y? This is 6. When x is 1, y is 6. When x is equals to 2, then y is 2 plus 5, that is 7. When x is equals to 3, then y is 3 plus 5, that is 8. So our relation is finally stands like this. It is 1, 6, then it is 2, 7, and finally it is 3, 8. So the relation in this roster form consists of these members 1, 6, 2, 7 and 3, 8. Now you can now very much easily you can tell what is the domain and what is the range. So the domain is equals to, as I told you, all the first elements in the ordered pairs of the relation. That is 1, 2, 3. 1, 2 and 3. This is the domain, and the range is the set of all the second elements in the ordered pairs of the relation 6, 7 and 8. 6, 7 and 8. Now here in this particular question, let the set A has elements 1, 2, 3, 5 and set B has elements 4, 6, 9. Define the relation R from set A to set B, and it is defined as all those ordered pairs in which the difference between x and y is an odd number, where x belongs to the set A and y belongs to the set B. Find the domain and range. So first of all, we just need to write the set in the roster form. The relation is defined given as xy is such that difference between x and y is odd and x belongs to the set A and y belongs to the set B. So let us define the relation as, if we move from set A to set B and such that the difference between the elements while moving from set A to set B is an odd number. So 1, 4, the difference of 1 and 4, that is if you take it as 4 minus 1, that is 3, is an odd number. So we can relate this 1 with 4. So you can write 1 comma 4, 1, 6. So 1 difference between 1 and 6, that is 5, is also an odd number. 1, 9, it is an even number. So now starting with 2 and 4 even, 2 and 6 even, to 2 and 9. So we have 2 comma 9. The difference is an odd number. Now starting from number 3, 3 and 4, difference is odd. Then 3 and 6, difference is odd. 3 and 9, it is even. Starting moving from 5, 5, 4, the difference is an odd number. 5, 6, the difference is an odd number. And 5, 9, the difference is an even number. So these are the elements of the relation, which are the members of the relation. And the condition that is defined here is the difference between the elements in the ordered pairs must be an odd number. So 4 and 1 odd, 6, 1 is 5, that is odd, 9, 2 is 7, that is also an odd number, 4, 3, 1, this is odd, 6, 3 is 3, this is odd number, 5, 4, odd number, and 5, 6 is also an odd number. Now let us define the domain. So domain is the set of all the first elements in the ordered pairs of the relation. So 1, 2, 3 and 5. 1, 2, 3 and 5. If 1 is repeating, we will take it only once. Similarly, range is set of all the second elements in the ordered pair of the relation, that is 4, 6, 9, 4, 6, 6. So it is 4, 6 and 9. So the domain of this particular relation comes to 1, 2, 3, 5 and the range is 4, 6, 9. Question number 7. Set A is 1, 2, 3, 4 and 6. Let R be the relation on set A which is defined by the ordered pairs AB, both A and B belongs to this set A, such that B is exactly divisible by A. So you have to write the relation in the roster form, find the domain of the relation and find the range of the relation. So first of all, let us write this relation in the roster form. So we need to take all those ordered pairs under the condition that B, that is the second element in the ordered pair, is exactly divisible by A. So 1, 1, if you take, so 1 is exactly divisible by 1. So 1 comma 1, 1 comma 2, 2 is exactly divisible by 1. 1 comma 3, 3 is also exactly divisible by 1, 1 comma 4 and 1 comma 6. So all these numbers, if you take it as 1 as A and 1 as B, it is divisible exactly. 1 exactly divisible by 2, then 2 and 4, that is 4 is exactly divisible by 2, and then we can take 2 and 6. 2 and 6. 6 is also exactly divisible by 2. Now, if you start with 3, so there will be 3 and 3, and 3, 6. Then start with 4 cannot be, and 6 also cannot be. So it will be, we can take it as 4 comma 4, and finally 6 comma 6. So these are the elements of the relation 1 1 1 2 1 3 1 4 1 6. Now 2 is divisible by 2, 2 is divisible, 4 is divisible by 2, and 6 is divisible by 2. So 2 2 2 4 and 2 6. So 2 2 and 2 4 and 3 6. Starting with 3, 3 is divisible by 3, and 6 is also divisible by 3. So this is possible. Now starting with 4, 4 is divisible by 4, 6 is divisible by 6. So this is the roster form. Now to find the domain of this relation, that is, if I am writing here, we are running out of space. So if you write it here, what is the domain? All the first element. So it is 1, 2, 3, 4, 6. All 1, 2, 3, 4, 6. Exactly the set A. Then relation. Range. Range is a set of all the second elements. So it is 1, 2, 3, 4 and 6. So both the range and the domain happens to be the same in this particular question. Looking into the next question, determine the domain and the range of the relation R, which is defined by R equals to, the ordered pair comes as like x comma x plus 5, where x belongs to this set. That means x has the elements 0, 1, 2, 3, 4, 5. These are the values which x can take. So for this relation, we need to determine the domain and the range. So first let us write the set in the roster form. So R is equals to given as x comma x plus 5, where x belongs to 0, 1, 2, 3, 4, 5. These are the values which x can take. So the relation stands like this. Starting with 0, if we put 0 here, so then it is 0 plus 5. So the first order pair is 0, 5. Then when x is 1, 1, and this is 6. So next order pair 1, 6, 2, 2 plus 5, 7. So next is 2, 7, with 3, 3 and 8, 4 and 9, and finally 5, and 5 plus 5 is 10. So this is 5 comma 10. So this is the relation starting with 0. If x is 0, then this value is 0 plus 5, that is 5. So 0, 5, when x is 1, so this is 1 and this is 6. So 1, 6, when x is 2, so it is 2 and 2 plus 5, that is 7. When x is 3, then 3 and 3 plus 5, that is 8. When x is 4, so 4 and 4 plus 5, that is 9. And when x is 5, then 5 plus 5, that is 5 and 10. So let us write down the domain. Domain, obviously the values are 0, 1, 2, 3, 4, 5. 1, 2, 3, 4 and 5. And the range is given by the second elements in the order pair 5, 6, 7, 8, 9, 10. This is 5, 6, 7, 8, 9 and 10. So this is the range of this relation, and this happens to be the domain of this relation. Let R be the relation on the set N, that is the natural numbers, defined by R equals to the ordered pairs AB. The condition given here is A plus 3B is equals to 12. This is the condition on the basis of which the relation is to be defined, where A belongs to the set of natural numbers and B also belongs to the set of natural numbers. So you need to find number one, that is R, that is the relation in the roster form. Secondly, the domain of this relation, and finally the range of the relation. Now the first thing that we need to do here is defining the relation in the roster form. So the relation is given as A comma B. We can write it as A equals to 12 minus 3B, where A belongs to the natural numbers and B also takes the values as natural numbers. So if you start with, so you can see here B and A and B are the two variables. The value of A can be obtained after putting the value of B. Now B, since takes the values of the natural numbers, let us start with taking the values of B from 1 and then we calculate the value of A. So here, when B is equals to 1, then A is equals to how much? When B is 1, so it is 12 minus 3 into 1, that is 12 minus 3, and that is 9. When B is equals to 2, so it is 12 minus 3 into 2, 6. So A is equals to 6. When B is 3, so 3, so 3 into 3 is 9, so 12 minus 9 is 3, so A is 3. When B is equals to 4, so that is 4 into 3, that is 12. 12 minus 12 is 0, that is A is equals to 0. Now you can see, when B is 1, A is 9, when B is 2, A is 6, when B is 3, A is also 3, but when B equals to 4, A is 0. Now in the definition, you have A is natural number. A takes the values of natural numbers, but here you have got the value of A as 0, which is not a natural number. So this particular ordered pair will not be included within the relation. Only those ordered pairs will be included with values of B are 1, 2 and 3. If you go beyond this, if you take 5, then 5 into 3 15. So 12 minus 15 becomes minus 3 as a negative value, which cannot be a natural number. So we can take all those values for which the value of B is 1, 2 and 3. So the relation finally stands like this. AB will be 9, 1, 6, 2 and 3, 3. So this is the relation in the roster form. Now finally we have the domain as the set of the first elements, that is 9, 6, 3, or you can write 3, 6, 9, and the range, the set of all the second elements 1, 2 and 3. So here it is, just have a look.